In this tutorial, we will do pick and place simulation using MoveIt, YOLOv8 OBB and Gazebo Harmonic. The robotic arm will pick up one bolt on the table and place it to another location. Here, usual web camera is located. In this window, image of the camera is displayed. Detected bolts are surrounded by blue bounding boxes. For bolt detection, we are using the model that we trained in the previous tutorial. By clicking on one of the bounding boxes, the robotic arm will move to the selected bolt, pick it up, move to another location, and drop it. Now let's see how we do it. To pick up a bolt, we should move the arm to the right position. For that, we should know the bolt's position. As shown in this image, we can obtain center coordinate of a bounding box and bounding box orientation using YOLO. Here is a coordinate system of our simulation world. Using perspective projection transformation, we can calculate coordinates of the detected bolt. For perspective projection transformation theory, please see this tutorial. In this case, coordinates of a bolt in a simulation world are described like this. Here, Cx and Cy are optical center. Fx and Fy are focal distances. By subtracting from U and V optical center, we convert image coordinates to camera coordinates. Then, by dividing it by focal length and multiplying by c, which is the z-coordinate of a camera, we can obtain coordinates of a bolt on the table surface. Since the camera is displaced by delta x and delta y from the center of simulation world coordinate system, by adding these values we can obtain bolt coordinates. Now let's see program flow. Firstly, object detection is done. The bolts are detected using YOLOv8 OBB. Bounding box coordinates of all detected bolts in the image are published using the YOLOv8 inference topic. This is done in the YOLOv8 OBB publisher script. Next, position and angle of the bolt selected by the user is calculated. This program subscribes to the YOLOv8 inference topic and the image raw topic. It displays an image obtained from the camera and bounding boxes of all detected bolts. Real-world coordinates of the selected bolt are calculated and published using the target point topic. This is done in the bolt selector script. Finally, we operate the arm. We use values of the target point topic to set arm goal position. Arm trajectory is calculated using the moveit-py library. This is done in the arm control from UI script. Now let's see the programs. Please download the MoveIt2 OBB zip file and extract it to your home directory. We will begin from the bolt selector script. In the graphic scene class, coordinates of the mouse and mouse button click action are detected. In the GUI class, in these lines, subscriber and publisher are defined. Here, timer is defined. Using this timer, we execute callback functions of the subscribers. We do this because GUI loop is already running. So, if we start a new loop using the spin function like in usual ROS programs, GUI will stop reacting to our further operations. In the YOLO callback function, here, we display the obtained image to the graphic scene. In the for loop, we draw a bounding box around each bolt. If mouse is closer to the center of the bounding box than threshold distance, we draw a red bounding box. Otherwise, we draw a blue bounding box. If mouse is clicked, position and angle of selected bolt are calculated and published. Now open the ARM control from UI script. Here, we import MOVEit-related libraries. Generally, MOVEit is used with CPP, but in this tutorial we use the moveit-py API, which can be used with Python. In the plan and execute function, robot arm trajectory is calculated and executed. In the controller class we obtain components on which we will do planning. Note that these components should be specified in the URDF file. In the move to function we set position and orientation and pass these values to the plan and execute function. In the gripper action function, we set position of the panda finger joint 1 joint. Note that we don't have to set position of the opposing panda finger joint 2 joint because it will mimic position of the panda finger joint 1 joint. Every time the controller receives the target point topic, the arm will begin to move in a sequence to pick the selected bolt and place it to the specified position. Now, let's see the launch file. Open the YOLOv8 OBB script. This file mostly resembles the launch file we used in previous tutorials, but there are few differences. The first one is that instead of the default Dart Physics engine, we are using the Bullet Featherstone plugin. This is because Dart Physics engine is not supporting mimic joints which we have used in the hand. The second difference is that we have to specify MOVEit-related setting files. These files can be generated using MOVEit Setup Assist, though we will not go through this process in this tutorial. In the controller setting YOM file we set a pipeline that will be used for planning. In this tutorial, we use a STOMP pipeline. STOMP stands for Stochastic Trajectory Optimization for Motion Planning. It is a probabilistic optimization framework that produces smooth, well-behaved collision-free paths within reasonable planning time. In this simulation I achieved the best results using STOMP Planner, but other planners also can be used. Open the Panda URDF file. Here we add the panda finger joint 2 mimic joint. This joint is not necessary for the arm model, but we need it to avoid the error described in this issue. Once this issue is fixed, this joint will no longer be needed. Now, let's run the simulation. After building the packages, launch the YOLOv8 OBB script. In another terminal, launch the YOLOv8 OBB script. Open one more terminal. Run the setup bash script using the source command. Then, move to the UI directory. Execute the bolt selector Python script. When UI window appears, select one of detected bolts. The arm will pick the bolt up and place it to another place.